Okay guys, so we're continuing our observer, and I'm gonna, after finishing this, I'm gonna write a comprehensive Matlab code that you can use after graduation. But before that, you have to complete that. So we saw that if you have the observer, it can be written as x dot hat is equal to a x hat plus bu plus ke that we have to determine, like, as this is the observer gain, and y minus cx, right? So you saw that I solved the example in the previous class. So this is observer gain, and the first method that we had to solve, that if you want to have a observer gain, so you have to solve this problem. The first method that I showed to you, it was si minus a minus kec, remember, in the previous class, minus kec, where you know that y is equal to cx, that's right, so, and y hat is estimated is cx hat. So this is equal to s minus mu1, s minus mu2, and 4, and say s minus mu3, for when the order of the system is equal to smaller than 3. So I solved the problem for you in the previous class. So this is the fundamental that I'm going to use in the Matlab coding, okay? So, but the second that you have seen in the state feedback control law was the Ackermann's formula for designing observer. Remember? Exactly because of the duality principle that I showed to you, whatever you have done for the state feedback control law, you can use for the observer. So remember that for state feedback, right? We were the gain k, we were determining in this formulation 0, 0, 0, 1. That's right, for the CISO system. B, A, B, A, N minus 1B. This was what? Come on. Yeah, controllability matrix M, that's right. Inverse in phi of A, and the phi of A was a polynomial. So exactly the same for the observer. For observer gain matrix, observer, ke gonna be phi of A. We are reversing everything because you are dealing with the observer, so we have to talk about the observability matrix, that's right. CA, and remember that we had this CAN minus 1 inverse, and this is the gain that we are talking about, 0, 0, and the 1. And what is phi A? Phi A, as we had for the state feedback, is matrix A. When I'm saying A, means this A, AN plus alpha 1 S, A n minus 1 plus alpha n. And how we define alpha n, if you remember? Exactly the same process. When you have desirable poles or eigenvalues for the observability, so you can get from here s minus mu n. These are desirable poles, that's right. Mu2 s minus mu n is equal to, it's gonna be Sn, gonna give you a polynomial, that's right. Alpha 1 Sn minus 1 plus alpha n. So you're gonna put these here, understand, as we did for the state feedback control. So now you know it's I solved one example, analytical example, by the direct method, and you can do by Ackermann, because exactly like as state feedback control law, we're going to use Ackermann formula on the Matlab coding. But in the final exam, you have to use this formulation first to validate everything, okay? But after graduation, go to the Matlab code. So now, let us see. Now we know what is state feedback control law, and we know what is observer. Is estimating the state variables that you cannot measure directly, or there's noise on them and it's not accessible, or you don't have the proper sensor to measure them, okay? So now let us see effects of adding observer on a closed loop system. That's right. Now I'm gonna combine observer with the state feedback control law. This is the most complete version that you will learn in this class. In the state feedback, we assumed x of t, state variables, is measurable. That's why we developed the Matlab code. That's right. We assume that we 100% are measurable, and we designed the state feedback control law. That's right. And are known, the state variable are unknown to be used in your U control signal minus kx. Assume that they are knowns, but we sometimes may not have some x of t's state variables because of the inaccuracy in the sensor or inaccessibility to measure them, and hence need to add an observer to the state feedback controller. So that's why you, as a control engineer, you're gonna have state feedback in your coding and the reality plus observer. Understand? So how you're gonna have two things. One of them is that x dot is equal to ax plus bu, but your u, knowing that some of the state variables are not measurable, gonna be minus k x hat. This goes here. That's right. But where we got this x hat? From whatever I taught. X dot is equal to ax hat plus bu plus ke y minus c x hat. So now your function is to determine this gain for the controller and this gain for the estimator or observer. So you have two gains that you have to design. By what? By theory that I taught you, and the acre or place that I taught you in Matlab. That's right. I'm gonna go to a comprehensive example this class or the next class. Okay. So hence, if the system is completely controllable, I taught you this, right? You have to write the controllability matrix, and See the rank of that matrix. If it is equal to n, your system is completely controllable and observable. You have to write observability matrix. See the rank of that. So go ahead. If that's the case, you have x dot is equal to ax plus bu, and the y is equal to cx. But when you have uncertainty in state variables, your u gonna be minus k x hat. That's right. So you can wait, this is freezing. Hold on. So if you plug this inside here, okay, I'm gonna see what's the combination of the observer and the controller. So this comes x dot is equal to ax, that's right, minus bk x bar, that's right. So you can write like this, guys. You can add minus bkx and add bkx, that's right, because this is 0 finally, minus bkx bar, that's right, and this is x, that's right. So you see that these two you can factor out what? X, so a minus bk in x, right? And now you can factor out here what? Plus bk, you can factor out x minus x hat. But what is x minus x hat in the observer? I told you this is e, remember? Error signal between the estimated vector and the real vector that you are measuring. That's right. So this equation you can write like this. X dot is equal to a minus bk in x plus bk in e. This e is for the observer, from error of observer. Error of observer, right? This is equation number 1. Equation number 1. If you remember from the previous class, part 19, go and see that we develop for the observer e dot is equal to a minus k e c e. If you forgot it, go and see. See the same e. These are the same e. That's right. So this is relation number 2. Now you can write 1 and 2 in the state space like this. Look at here, x dot, this, e dot, right? X dot, e dot is equal to, so your state variable here is what? X and e. X, e. That's right. Let me fix this. Is it recording? Yeah. So your x is a minus bk, first line. Your e is bk. Second line, question number 2 is 0. You have e. A minus KEC, and these are the gains of the controller K and the gains of the observer that you have to determine. That's right. So this is your state space, right? Let me go to the next page. So you see that I combine the control observer with the state feedback. So now let us define Z, capital Z, sorry, boldface Z, as your X and E, state vector of X and E. Sorry, and let me call AN as a minus bk and the bk 0 a minus kec. So if you look at here, guys, this equation, this is gonna be z dot. That's right, this is gonna be z dot. What you get is z dot is equal to an in z. Have you seen this? Yes. Beginning of this course, when I was teaching you x dot is equal to ax. Remember? Matrix exponential. Remember? So this is the same. Sorry. So hence for a stable observed state feedback. Why together? Because we have state feedback and observer at the same place. So I'm just putting on the red box, stable observed state feedback. Controller the characteristic equation what is the characteristic equation of this for this? Look at the an. Now you know direct method, that's right. Si minus what? Yes, a minus bk 0 and a minus kec, that's right, 0. So if you do that, what you get is si minus a plus bk minus bk 0, si minus a plus kec is 0. So you get this determinant of this, for God's sake, is si minus a plus bk in si minus a plus kec. Oh, what happened? Kec is 0. Is 0. This is the classic equation, must be stable. Right? So it says these are the poles of, let me change the color. These are the poles of state feedback and the pole placement for observer. So the closed loop, so closed loop poles are poles of pole placement for the state feedback, as we have done by example in Matlab. I'm gonna do again, plus poles of observer. We're gonna place desirable poles for state feedback part, and we're gonna place the poles of the observer. Okay, and so by saying that the state feedback and observer designing are what? As you can see, I'm gonna do in the MATLAB code, independent, they are independent. Okay. Understand? So let me go to a comprehensive example. Maybe it takes this class and the next class. Okay, let me see if I have time. Come on. Yes, I do have. So this is the example that you're gonna see in industry. This is the simple example. This is the famous example I showed you several times from undergraduate vibration and control until today that you are in this class. So this is mass spring and damper, K and C, and I'm gonna design the MATLAB code in two cases. One of them is that you wanna push mass from non-zero position to origin, as I taught you in this class, and to non-zero position. This is number one. Number two, non-zero position. So in the first case, I'm gonna stretch this mass, say for here, then I'm gonna release, and I want it goes back to x0, but based on my desirable poles and the assumption that I cannot measure the velocity and even say position of the mass, because I don't have any sensor. Who knows? So what I'm gonna do, and this is your U, right? The first case is that I'm gonna say x at time 0 is 0.3, because it's here, say it is 0.3, and x dot at time 0 is 0. I'm releasing from the rest, and having that, we know that from the undergraduate dynamics, the equation of the motion for this gonna be U. And as I taught you in this class, this is very trivial. I'm gonna say m1 is x and the m2 is x dot. So dm1 gonna be m2, as I'm gonna transfer to MATLAB, and the dm2 gonna be minus c m2 minus k m1 plus u. That's right. So first of all, we know that the u, because we need observer after time, is kx bar, because we're gonna estimate that we don't have it because of lack of the sensor. So we have two sets of equation. Another is that I taught you, x dot hat is ax plus bu x bar bu plus ke y minus cx bar. So exactly they are the same, but we are estimating. That's right. So now I'm writing here. That's right. So a from here, you see that from here, a matrix gonna be what? A matrix is 0 1 and minus k minus c. That's right. And the b, it is what? Single input, single output is 1 over assuming that the m is 1. This m is 1. Is 0 and 1. That's right. 0 and 1. So this is equal to, I'm going to write like this: 0, 1 minus k minus c in estimated. I'm saying dm3 is dm4. dm3 means, look at here, this can be written as x hat dot 3 x that hot bar 4. See, these are this side is equal to, in x, here you're gonna write like what, gonna be m3, right, and in m4 plus bu, b is 0 and 1, and u that we had from here. So you see your u gonna be how much based on whatever I developed here? Minus k, right? Your x gonna be m3 and m4. That's right, because now you are using estimated state vectors. That's right, estimated, plus ke. So ke, I'm gonna show in the Matlab code. Your y is cx. Your c, I'm saying I want to measure the both of them, position and velocity. That's right. So, and y gonna be cx, the real x. So this gonna be 1 in 1, and gonna be what? Come on, you tell me. M1 and M2. They are reals that you are measuring. M1 and M2. So this is y. Again, c, this c, but this is x bar. Gonna be what? Come on. Yeah, M3 and M3 and M4. Here we go. Right? So now you can say, you can put the first line of this here, the second line of this second row here. I'm going to show it in Matlab. Okay. So let me go to the Matlab if I can finish it. Hold on. Okay, so here we are. So I'm gonna open this. Do with me at home. I'm gonna say function state variable dm is equal to I'm gonna say mass spring damper. The problem is t and m time and state variables. So I'm gonna say dm, because we have 4 state variables. 2 is for the measured real, real that we have, and these are for estimated. That's right, these are for estimated, the same equations. So where we are, so I have 0, zeros, 4 and 1. That's right. I'm gonna say k is, I don't know, 1 Newton per meter. C is equal to 0.2, damping. I already said m is 1. I don't want to involve it here. And now you're gonna have dm1 is equal to m2, the equation of motion of that, and dm2 is minus c in m2, that's right, in k, in, as I wrote, in m1. What the hell is that? That's right, in m1 plus your u. But your u, let me first MS696 MSD, that's right. What is that? No. Yes. I don't know when. Oh, this is MSD. I'm gonna fix it later. So your U is what? minus k gain of, I'm gonna say gain of state feedback in, but you see here not in M1 and M2 minus kx, in what? In M3 and M4. So you're gonna see that in your estimated, your observed, you're estimating in M4. See? Now I have to go to what? To your estimated M3 is equal to DM4. So you see that this U, your state feedback, are getting the estimated variables. But as I taught you, as I wrote here, is AX plus BU plus this. So first of all, you have to write your A matrix. A matrix, as I said, is 0, 1, minus K, and minus C. That's right. See here for this problem. So using the Ackermann formula, that's right. Minus K minus C. And your B matrix, 0 and 1. Is 0 and 1. That's right. And your B is 0 and 1. And now, as I taught you several times, and you have seen K state feedback is Acker, A and B, and J of state feedback again. That's right. But you have to say J. Suppose that you wanna have critically damp behavior of your mass when it backs to the origin. So it is -2 and -2. So we have to have repeated negative poles, right? J of what? State feedback, right? So now you have it, your KSF. So you have it, A and B, that's right? This is this. So now let us go here. So DM3 and DM4. These are the state estimated that we're gonna use in the control law. So I'm gonna say a right hand side. I mean this, guys. I mean this. See, this is right hand side. Right hand side is A in what? A in estimated M3, M4. M3 in M4, not the real ones. Okay, plus B in U, because your U is here. We just wrote it down, and we B have here. Plus K of estimator. That's right. Look at here. K of estimator. Y. Let me define Y here. Look at here. Y is equal to, first you have to say your C. Suppose that I want to estimate both position and the velocity. You can do whatever you want. Y is equal to C in what? Real one. Your Y first is real one. This is the estimated one, that's right. So you're gonna have C in what? M1 and M2. That's right. And now Y hat is the same but for estimated. See the difference? Right? So M3 and M4, M3 and M4. Here we go. Right? Now again, KE multiplied by what? Y minus Y hat. That's right. So gonna be KE multiplied by Y minus Y hat. This is your right hand side. So you're gonna say now right hand side, first row, first column, obviously. Right hand side, second row, first column. Now you have estimated M3 and 4 state variables, right? Understand? First of all, let me close this. Let me run this to change the direction. Okay. Second of all, let me close this because the names must be the same here. Here must be MSD. That's right. So, and again, I'm commenting here that we assume mass is 1 kilogram. That's why I removed mass from my equations. Understand? So let me now double check everything, and C is -2. Okay, so we got KSF. This is what? This is, I'm writing, gain for state feedback. Now this K of estimation also we have to determine. How? K of estimator, as I taught in the previous class, again we're gonna use Acker, A and C. I'm gonna intentionally see like this because I want to show the error. That's right. And J of estimator. Okay guys, what is J of estimator? J of estimator, the desirable pose eigenvalues for the estimation. That's right. Can I make it under them? Am I stupid to intentionally oscillate the estimation of state variables? No. So I'm going to put -5 and -5. That vanishes fast and estimate as a critically damned behavior. Understand? And the C, we have it. Because again, here you have A and B for state feedback, and here is A and C. Look at here, based on exactly what I developed, guys. Here we go. See here? Come on. See? A and B, A and C. Understand? This is super important. Okay? So now why I keep it C? Because I wanna work with that. So I'm gonna now take a solver. T and the total output is ODE 45 at MSD, time between 0, 1 and to 10 seconds. How many state variable I have? How many state variable I have? 4. 2 of them is for the real measured, is for the estimated. So, but I'm gonna release the system from 0.3, as I said, velocity, and I don't know the measured because it's trying to estimate. So I'm gonna say I put at 0.2. Understand? Put at 0.2 and 0. Because I don't know it. I'm gonna play with that. And let me close this because I don't want to show it. So figure one, plot T and Y, the real, bold, that's a blue, hold on, this is position of the mass. That's right. Now estimated position of the mass, because I don't know, okay, gonna be Y2. Oh, sorry, Y3. And I'm gonna save it as solver of MSD. Okay, solver of MSD. And I'm gonna make it red. And I'm gonna make it grid. Okay? First of all, when I run it, what I expect to see? Let me debug it. Yes, error. What's the error? It says in line 23, the matrices must have the same number of the rows, because your C I intentionally kept as C, that's right? Your C is 1 row, this has 2 rows. So you have to put these guys as transpose when you're designing observer. Please do that, okay? Transpose C. You have to just flip, that's right? So that has intentionally I did it. So if I pause, I'm gonna just pause here your code because I want that you see it. And I have another pause. I want to just do it here. Pause. Okay. Now if I now run it, okay. Okay, see? The gain of the state feedback for this under damp behavior that I want the mask go to origins. And if I see it, this is estimator gains, right? This is like that. Understand? So they are completely independent, as I taught you. Understand what I'm talking about? So I'm going to just stop it because I don't want to. Okay. So now everything is right, hopefully. Huh? Oh, I also want to show this before going to the results. That's why I stopped it. Okay guys, look at here. This is the gain of the state feedback. Gain of this. And YH, oh, there's a typo here. Hold on. It's good to debug it. Where is that? YH. Oh, this is underline. I just want to show it again. So you see that this, you see that RHS has first line goes to DM3, second line goes to DM4. That's what I wanted to show you, okay? And now I'm going to stop it. Understand? That's why I wrote it here. First line of right hand side, second line of right hand side. Second rows of the right hand side. Okay? Now let me delete all of these. So now let me put this gain of observer. Okay, and let me delete also this. Do you have another pause? No. Now look at, see what's happening. First of all, this blue line is for the real, right? This is for what? The estimated. First of all, this is not enough. Maybe I have a typo. I have to fix it. Guys, let me double check with you. This diverges. I have some typo. Let me debug it. I'm stupid, guys. Look at this typo here. Must be minus. Okay. Yeah, it must be minus. Let me double check this because it happens. Okay. So now let me take it back to 10. So let me see. Yes. See, guys, this starting the real is from going back to 0 eventually, and this is the red one is estimated. That's right. See the difference? This is estimated position of that. So we designed the observer. Okay. And now I'm comparing it together. So let me see. This is because I said the both of them. I said, look at here, the state feedback must be critically damp, and this is also critically damp. So they have this kind of things. They have this kind of see this 0.3 after 15 seconds goes to 0 to origin I wanted, and this is the estimated finally goes to that. So I estimated that. So and your control input is based on the estimated that you don't know. Okay. So if I plot the velocity to estimate to see the between the real and the estimated, figure 2, this is for the real, this is for estimated. Let me see how it works. See, the blue line is for the real, this is for estimated. Understand? And the both starting from 0, right? Now if you can say 0.2 and 0.2, let me see what's the effect for the estimation part. See here, when you do desirable poles, you decrease the number to -2, it goes much faster converge to the real position of the mass. So we did it. Okay, so let me say legend legend is x1 and x1 estimated estimated, and the same here to make it understandable. dx1 velocity and dx1 estimated. Look at here. Oh, look at here. See, this is for the observer based velocity, this is for the real velocity. So, and this is for observer based position of the mass. This is what? Now if you even increase say this is, I don't know, maybe it is at 0.1 and I don't know, its velocity might be 0.5 because we don't know, right? So let us see how it performs. See, the velocity is starting from 0.5. That's right. See here, this is 0.5. Finally, by estimator that we designed, but gain of estimator kind of goes to 0. And now it said this, the position of the mass from 0.1 finally has a DS overshoot and finally goes to the origin. You see, but even you claim that I don't know, I don't have sensor, but design a controller for me, it can do that. Now let us look at the controller. Okay, now if you want to say, okay, before going that, you want to say, you know what, I want to have underdamped behavior. Let me put it again 0 and this is 0.2. Underdamped behavior when going back. So let us see what it does. Here we go. Okay, this is underdamped behavior as it does. Okay, so here we go. Now we can, as I talk to you, you can plot the control inputs. You can say u plot con is equal to u. I want to plot it. So you're gonna have global, as I taught you, con u. Then you're gonna say con is equal to con +1. Please go to previous codes that I developed. You're gonna have the same here. That's right. You're gonna have, and you're gonna say con is 0. That's right. You're gonna have con is 0. And now you can plot the control state feedback control law that you design based on the observer. Figure 3, and let me just, here we go. T and U. Greet. Hopefully I didn't make a mistake. Not U, sorry guys. UP. Why I said U. UP. And this is UP, right? So if I say that, what's wrong? Where's typo? Oh, the same things because they have no step size. So I'm gonna say, remember that I did this previously? Time is t, right? Remember that I have done, and this is time, and this is time, right? So here is time. Here we go. See, this is the control input based on the observer. Because u is equal to minus kx hat. See that this kind of sharp edges because it's estimating. Understand? So I'm going to stop it here because I'm going to develop this more and more, this code. Okay.